Alrighty, welcome to this next video. Today we're going to be talking about the lungs. So, first, what allows us to actually breathe? Well, that's a great question. If you think of our lungs like this, right? You got the bronchi, I guess your trachea, and then the bronchi, and then those go into alveoli. So you got a couple membranes and pressures that allows this to work. First off, directly on the lung, it's basically like part of the lung, just like a covering of it. It's called the visceral pleura. And then on the outside of that is what we call the parietal pleura. And the inside here is the intrapleural space, or just the pleural space. You can say that as well. Now, what's really cool is this is lined with fluid here, and that allows these two membranes to stick together. And it's also not open to air. And so what that means is if this parietal pleura gets pulled on and gets pulled out, then that will cause an increase in volume in this space. And we know that volume and pressure are inversely related, and so that will cause an increase or decrease in pressure. So this will be further move more negative. That will then cause the visceral pleura to move with the parietal pleura and expand more. And that will, of course, tug on the lung and make the lung get bigger. So this is why it's called negative pressure ventilation, because you're having negative pressure here on the visceral pleura. Now, what this also means is as the intrapleural space gets more negative, the alveoli here also get more negative, because if they expand, then that decreases the pressure, and that decrease in pressure causes all the air that's outside of our body to come into the body, because air moves from high pressure to low pressure. And if the alveoli become negative pressure or lower pressure, then that would cause that air to come in. Okay. Great. Now, pneumothorax can cause some issues, because if this space right here is not open to air, or if it is open to air, normally it's not open to air, but if it is open to air, then that means that the pressure inside of here will increase. And the vacuum there won't be a vacuum, there won't be negative pressure. And so if the parietal pleura gets tugged on, the visceral pleura won't be able to move as much. And so if this area is open to air, that significantly inhibits a person's ability to inhale. Now, you can still exhale, right? Because once these alveoli become full, they get higher in pressure, and air moves from high pressure to low pressure. And so if the lungs is relaxing because of its elastic recoil, if it recoils on itself, then that will cause the pressure to increase in the alveoli, which will cause the air to go out. And so pneumothorax can occur in a variety of ways, right? So you can get shot in the lung, right? Shot in the chest. There'll be a little hole in your lung that will allow air to come in. You could also have a bleb, which is when one of the alveoli fuse to the surface of the lung, and that can cause a rip in the visceral pleura, which will cause it to be more open to air, and that will make the pressure within the pleural space higher, which will inhibit your ability to breathe, because this thrives on negative pressure, because that allows the visceral pleura to follow the parietal pleura and expand more. Now, inside of these alveoli, there's also some fluid. Now, normally there's a lot of water as well, just because the inside of our body is moist, it's wet. And so what this fluid does, and here in the green, it's surfactant, and it breaks up the interaction of the water molecules. Normally, if you didn't have surfactant, right, there would be you have your alveoli, and you'd have a bunch of water, and this water would want to tug together because of its surface tension, and that will cause the alveoli to want to collapse in on itself. And so that would make it significantly harder to breathe, like to breathe in, right, and expand, because increased surface tension increases the pressure. And so if there's higher pressure, then that's harder to inhale, because you want the pressure within the alveoli to be negative in order for the air to flow from a positive to negative pressure. Okay, now the surfactant breaks up the water molecule and it decreases surface tension. So that allows us to breathe a lot easier. It decreases the pressure, and so when you breathe, it's a lot easier to breathe in because it's easier for the alveolus to expand. Easier for it to expand because there's less surface tension. So if there's no surfactant, you can imagine that it'd be harder to breathe in, right? Now, this is kind of all explained in the Laplace's law, which is P equals 2T over R. Now, R is the radius of the alveolus, and what this is just telling us is that smaller alveoli typically will have higher pressure, but because of surfactant, that's not actually a factor in the lungs, because the surfactant kind of matches the amount. So really the main lesson that we can get from Laplace's law is that an increase in surface tension leads to an increase in pressure. If you increase surface tension, you increase pressure. T stands for tension, right? And so the less surfactant you have, the higher the pressure is, which means the harder it is to breathe in. Now, there's another really cool equation that we have for the pressure of oxygen in the alveolus. Now, it's typically, well, first it's the fraction of O2 within the air, and then it's the pressure of the atmosphere minus the pressure of H2O minus the pressure of CO2 in the arterial divided by R, which is the respiratory respiratory ratio. So basically, R is closer to 1 if you have more carbs, and it's closer to 7 if you have more, 0.7 if you have more fats. Now, this can be used clinically because typically this should be 100, or around 100, 102, 104. So it should be around 100. And the fractional oxygen percentage is typically 0.21. And you got 760 minus 50 here. And then CO2 is usually 40. And the R is 0.85 normally. Now, if this is not what we'd expect, that means there's some problems. And that's helpful for us to know, right? If we plug all these numbers in, we don't get the right number, then we know there's something wrong. And that can tell us as well how we can help them for now. Because if this number of PaO2 gets too low, then that can cause some really bad problems. And so we can know that if this number is really low, then we should give them more oxygen. So you can put them on oxygen to increase the fractional percentage of oxygen, and that will allow their PaO2 to be higher, which will allow them to live for longer, which is a great thing. Great. Now, within the blood, this is an alveolus, right? And then you got the blood here. The way that, I guess, of course, oxygen travels in, and then CO2 travels out of the blood. Let's make that a different color, actually. So, most of the oxygen travels in blood cells, as we know. Now, the important thing about blood cells is that they have hemoglobin, and each hemoglobin can take 4 oxygen, and that represents about 98% of the oxygen within the blood. Now the other 20% is the 100 millimeters of mercury that you got out there. So the oxygen comes in, and then it mostly binds to hemoglobin, and then keeps coming in until we get to these amounts. Now CO2 can also bind to hemoglobin, and what's cool is when it binds to hemoglobin, that actually causes more oxygen to come off of hemoglobin, which we'll talk about in a second. But CO2 can bind to hemoglobin. That's not very much. That's like 7%. Most of it is in the form of bicarbonate. Right, remember that equilibrium ratio? Most of it's in the form of bicarbonate due to carbonic anhydrase. There's about 70% there. Oh, I'm sorry. This is not 7%. This is 23% actually is bound to hemoglobin. And only 7% is the 40-ish millimeters of mercury. So that's kind of how it's all split up. This is how the carbon dioxide and oxygen travels in the blood. Now, when you get to the tissue, well, how does the tissue get the oxygen that it needs if most of it's bound to hemoglobin, right? So, sorry, this should be 2%. First off, we have this hemoglobin saturation curve. And it looks something like this, right? You got hemoglobin, you got the percentage of O2 saturation of hemoglobin. And then over here you got the P, pressure of oxygen. So as the pressure of oxygen goes down, right, which would happen in the tissues, then the percentage of O2 attached to hemoglobin decreases. And that's great because that means that in low oxygen environments, hemoglobin releases oxygen, which is exactly what needs to happen when you go to muscles and tissues and things. And there's ways that the body can make this happen even more efficiently. Because if this curve were to shift to the right more, then that means that it would be able to do something more like that. And the hemoglobin would release oxygen faster. Now, the way that this happens is hemoglobin has two states. It has the T state or the R state. And in the T state, there's less oxygen. It's harder for the hemoglobin to have oxygen. And things that contribute to the T state is an increase in CO2, an increase in 2,3-BPG, an increase in protons or acid, which would be a lower pH, an increase in temperature. Those all contribute to T state, which would cause the hemoglobin dissociation curve to move further right. Because all of those influence the T state and cause the hemoglobin to have a lower affinity for oxygen. I think that's it. Thanks for listening.